let's talk about buffers. And buffers are quite important because they help a cell, for example, to maintain the right environment. So that, for example, all the proteins can work properly. And with buffers, let's get started with something very, very simple. Last week, we discussed how a weak acid reacts in a solution. So, for example, we said we have HA, that's our acid, plus water. And if we wait long enough, then this thing will dissociate and it will establish a sort of an equilibrium. And we will talk about equilibria a little bit later in the year, what it actually means, an equilibrium. For the time being, we'll just simply say it is H3O plus A minus. We said that is our acid. What's that? Loud? Say. It's the conjugate base, exactly. And I told you last week that the easiest way to deal with the acid and the conjugate base is that the conjugate base has one proton less than the acid. Right? I've seen some people doing the quizzes and, not sure about that. So very simple. You have an A minus and an HA. The difference is one proton. And that is what makes it a conjugate base-acid pair. Now here's a question for you. What would happen, for example, if I increase the concentration of HA? What happens if I increase of HA? What would happen? The pH would increase, yes. What pH would? Increase or decrease?
Well, you're technically going like small. Oh, no, yeah, decrease. Yeah.
Decrease or increase? pH? Decrease. Decrease. What? D or in? D. Decrease. pH would decrease. What else would decrease or what increases? Loud? pOH increases. Yeah, that's true, because the pH decreases, yeah. What else? Just look at this thing here. H2O? H3O increases. Yes, very good point. H3O increases. Why? The reaction, the sort of the equilibrium, want to escape the force. Yeah, that's called the principle of Le Chatelier and Brown. It wants to evade this pressure from the HA. What happens to the A minus? A minus increases as well. Exactly. So just by increasing the HA, a lot of stuff is going on. What would happen if I increase A minus? By the same token, the pH increases, yes. pOH decreases. What happens to HA? HA increases. So HA would go up. Because again, the equilibrium wants to escape this pressure that we achieve when we add A minus. Now let's write that down again as our, as our reaction. And we said we can establish an equilibrium constant, that's this Ka, equals H3O plus times A minus divided by HA. And usually the water, we don't take that really into consideration. It's usually sort of built in this Ka. What was the concentration of water again? 55.56 bananas? Molar. Thank you very much. So we can, because it's always a constant, more or less, we don't even ignore that. We just don't do anything with it. So we have our equilibrium here. And what we have seen, this equilibrium constant is, as the name says, it's a constant. So if Ka is very big, is it a strong acid or a weak acid?
Strong acid.
It's a strong acid. Why? You are right, but that doesn't convince me.
Well, you've got, you should have a higher number on the top than the bottom.
So Ka is big. Your argument is that H3O plus and A minus are big, and I abbreviate it like that, and HA is small, right? Because if you divide something big, divided by something small, it's big. Yeah? So Ka is big, therefore the acid is strong. Okay? Beautiful. And it's a constant. So if I was to increase, let's say, HA for one reason or the other, if I double it, then I have to double this part here as well. Otherwise, it wouldn't stay constant. Okay, so what does that mean? Actually, by messing around with A minus and HA, with these guys here, I can actually change the pH of the whole thing. How? Well, let's just simply write that down again, because it's so nice. Ka equals H3O plus times A minus over HA. I've just written it in a slightly different format. It means exactly the same. And now I do, again, one of these dirty tricks that I like. And I take both sides, minus log. So what do I get? I get minus log Ka equals minus log of H3O plus times in logs becomes plus minus log A minus concentration, that's the base, over the acid. Okay? So far, no miracle happened. What is minus log Ka? It's pKa. What is minus log proton concentration? pH. Oops. Plus times minus gives minus. Minus log base over acid. Okay? We just rearrange that a little bit. That looks a little bit... Oh. We just bring that to the other side. And we have pH equals pKa plus log base over acid. Or you can write that in a slightly different form. You can write this as pH equals pKa minus log acid over base. Which way around you do it is totally up to you. Whether you have it minus acid over base or plus base over acid, entirely up to you. It's exactly the same thing. Some people find it easier to remember this one here. Because they say Peter Klapper is a positive bastard. Right? So if you want to remember it like that with this mnemonic, I just, get a little bit miffed when you write that in an exam. Because other people see it, and if it says Peter Klapper is a positive bastard, then I might get problems with my boss. What have you done to this poor little student? Now, this is actually quite an important equation. What you see here in both forms, but obviously you have to remember only one of it, because the other one immediately follows of it, has a name. This thing is called Henderson-Hasselbalch equation. Mind you, it is Hasselbalch, not Hasselblad. Hasselblad is a producer of a very expensive camera. So it's Hasselbalch, not Hasselblad. I've seen that in an exam paper. And the comment from the external examiner was, "What on earth are you teaching them?" Actually, it wasn't "what on earth," but I can't say that, what the examiner said. Now this Henderson-Hasselbalch equation, we can do quite a lot with that. Let me write it down again, because I love it so much. pH equals pKa minus log acid over base. What does it do for us? Why on earth am I going to, am I, torturing you with that? Well, actually, what this beautiful equation, and I hope you can see the beauty of this thing. What it does, actually, it tells us a relationship between the pH and the ratio of an acid to a base, its corresponding base. So what we can do is, for example, we can mix an acid. We can mix an acid and a base together. Acid and base mixed. And as a result, we get a certain pH. We can adjust the pH. So that's really nice. Now, what we usually do is we mix these things together and we have a certain volume that these two things give us. Quite nicely sometimes we don't need to deal with the volume because we can just simply say, here we have the concentration, and the concentration is defined as mole per volume. But if we have everything in one pot, then the volume is the same for both. So we can actually quite frequently deal with it in that we say we need the mole of acid divided by the mole of base. Okay? So, why is it called a buffer? Well, let's see what it does. pH equals pKa minus log mole acid over mole base. First of all, what would happen if I have the same amount of mole acid and base? What happens? Bless you. Say it loud. Did you hear that? Come on, Jessica.
pH would be equal to pKa.
The pH would be equal to pKa. pH equal pKa. Why?
Because it would cancel out the moles of the acid and the base.
Yes. What would you get for mole acid divided by mole base?
And then you get 1.
You get 1. Okay. So, if you have the same acid and base, this one here would be 1, right? So, you are absolutely right. This would be 1. Log 1 is 0. So, pKa minus 0 is still pKa. So in this case, pH equals pKa. That means if we take the same amount of acid, the same amount of moles of acid, and the same amount of moles of base, throw them in a pot, add water, mix. We get a pH which we actually can predict. We can predict the pH because we know that the pH is the same as the pKa. And for the pKa, we just simply look it up in a table. Yeah? Make sense so far? Fantastic. So, pH equals pKa. What would happen if I have 10 times more acid than base? What happens to the pH? I've got more acid, right? What would you expect for the pH? Talk to each other. What happens?
No, because the minus log is of that. It's not minus log 10.
What happens?
Put in the pH bar.
How much?
By 10 times? By 10 times?
Nope. What happens?
pH decrease.
Good. How much? Ah. Okay. Have you convinced yourself what's going to happen? What happens to the pH? It decreases. pH goes down. Absolutely right. Does that shock you? No, because you added more acid, and we know if we add more acid, it becomes more acidic, so the pH goes down. How much does it go down? 1. What? Banana. Okay, let's have a look. We now have log 10 over 1, basically. Yeah? Log 10 over 1, that's 10. Log 10 is 1. So now the pH is pKa minus 1. Yeah? Make sense? So if my pKa was, let's say, 3, and I whack in 10 times more acid, the pH goes down from 3 to 2. Yeah? Are you happy with that? What happens if I throw in 10 times more base? 10 times more base, what happens then? The pH would increase by 1. pK plus 1 if I've got 10 times more base. Yeah? Fantastic. Now, let's write it down again. pH equals pKa minus log. For some reason, I go always for the minus. I don't know why. It's just so sort of simply ingrained in my brain. But, you know, please feel free to write plus and base. Mole acid over mole base. Let's say we have a pKa of 5. Let's say we have mole acid is equals to 0.1 mole. Mole base equals 0.1 mole. What's the pH? 5, exactly, because it's the same. Acid and base is the same. Log the same, log 1 equals 0. We just discussed that. Okay. Now, let's assume I have done that in 1 liter. So that's my concentration, yeah? I just write it something like that. So we've got 0.1 mole acid and base. Now let's assume I add (0.02 mole of an acid of HCl. Okay? 0.02 mole of an acid. What happens? Try to figure it out. Talk to each other. What's going to happen in this case? Did you get it? So it's 0.12 over 0.008.
Did you get?
No, I didn't. Oh, yeah, because you got a minus in the other one, haven't you?
What's happening? What's happening? Look at this equation again. That's our starting equation, isn't it? We said at this stage, this is absolutely fine. This is our equilibrium. But now we add, from the outside, we add additional protons from our HCl. Yeah? What will happen? Which direction will this equilibrium move? It goes back to the left. So we get more HA. And what happens to the A minus? It decreases. A minus decreases. And HA increases. So how can we take care of that? Well, we can say our 0.1 mole, that was original, and that is original, 0.1, That gave us a pH of 5, we said. Now, how much did the acid increase? We know that because we added 0.02 moles of acid, so it increases from 0.1 to 0.12. These 0.2, these are from the 0.02 mole of acid. Yeah? Because we said our HA goes up. What is the base? What happens to that? Sorry?
Does it still remain?
Does it remain? Does it remain?
I think it decreases.
It decreases. Ah, good. How much? What do you reckon? How much does it decrease? You are absolutely right. But carry on with this thinking.
If you divide 0.12 by 0.1, which is the mole base, then you get a lower value.
Look at that. Look at that. We added protons here, right? Now these protons grab the A minus and become the HA. Yeah? Does that make sense? These additional protons grab the A minus, grab the base, and become HA. So therefore, HA goes down by the same number of moles that we added these acid, that we added the hydrochloric acid. So in this case, it would be, it goes from 0.1 to 0.08. Yeah, 0.08. Why 0.08? This is basically 0.1 minus the protons. Yeah? Make sense? Mm-hmm. So what happened? Our new pH is actually pH equals 5 minus log 0.12 divided by 0.08. Can somebody please calculate what the pH in this case is? You've done that, Jessica? pH equals 4.83. 83. 82. 83. Yeah? So the pH went down. That was not completely surprising because we added acid. It went down to 4.83. Who gives a damn? Well, actually, I do, because let's just simply calculate what would happen if we add 0.02 mole of acid, of a strong acid, HCl, in 1 liter. What's the pH of that? pH equals minus log of, this is 0.02 molar, 0.02. Can somebody calculate, please, what is minus log 0.02? You've done it? No?
1.6.
What is it?
1.6.
1 point?
1.6.
So the pH equals 1.6. 1.7?
1.70, I would say.
1.67.
Yeah.
Yeah?
1.69.
1.69, okay.
Like round at 1.7.
It's sort of like the, an Oriental bazaar. 67, 69, 70. Yeah, okay. You get the gist. So 1.69. Do you see actually what happened here? If we add our hydrochloric acid just to pure water, the pH would be 1.7. If we add the same amount of hydrochloric acid to our buffer system, the pH would only go down from 5 to 4.83. So this buffer system, made up from the acid and the conjugate base, protects our system from huge pH differences. This is exactly what you want when you don't want any change. And trust me, cells hate change. They don't want any change because it could be absolutely devastating for them if there is change. So cells have to maintain a stable environment. That is why these buffers are so absolutely essential. And as I said, the buffer is made up of an acid and the conjugate base. If we add an acid, if we add protons, then obviously HA would go up slightly. The base itself would go down. Yeah? Okay, now here let's think again about it. pH equals pKa minus log mole acid over mole base. We said mole acid equals mole base equals 0.1 mole. Okay? What would happen if I add 0.05 mole of NaOH? Which one increases, which one decreases? Say loud. The base increases, what happens to the acid? Decreases. So we go from 0.1 mole acid, we go to 0.1 minus 0.05 gives us 0.05 mole. 0.1 mole base goes to 0.15. And we get 0.05 divided by 0.15. Can anyone do the honors?
Oh, the answer?
Yeah?
5.48.
5 point pH equals 5.48?
Yeah.
Thank you. So you see, it works in both ways. If I add acid, it goes down, but not dramatically. If I add OH minus, it goes up, but not dramatically. So the buffer does exactly what it says on the tin. It buffers the system against these fluctuations. Okay. pH equals pKa minus log mole acid over mole base. We add, so we've got 0.1 mole for the acid and base. We add at 0.1 mole of acid, of HCl. Oh, for heaven's sake. Okay, predict what's going on, what's happening. There's no base. So what's happening? Okay.
Wouldn't it just be minus log 0?
We are getting into log 0.
We know that's not possible.
So, wait a moment. Okay. We move from 0.1 and 0.1. We move. The acid increases to 0.2. The base moves from 0.1 to 0. Okay, so what is log 0.2 divided by 0? Error. Error. It goes beep, 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 beep. The system can't cope with that. It's not just that the maths can't cope with it, it is the system can't cope with it anymore. It basically means we have reached the limit of our buffer. The buffer can't cope with it anymore. The limit of the buffer. This is also called the capacity of the buffer. That makes sense. If we overstep the capacity, then the whole system falls apart. We can't deal with it. Usually, buffers work best if it has a high capacity is high, and the pH the desired pH is pKa plus minus 1. In this range. That is where a buffer is good. So for example, blood has a pH of 7.2. It's absolutely essential to keep blood at a pH of 7.2. If it goes down to 7, you're dead in the long range. Right? We have different buffer systems available. We might have an acetate buffer. Here the pKa is 4.75. We have a carbonate buffer. And the pKa for that is 6.8. And we have a phosphate buffer. pKa is 7.21. Which one of these three buffers is unsuitable to protect us from any damage? Acetate. Why? Because this acetate buffer would be best between 3.75 and 5.75. But that's not where we need it. Yeah? Can you imagine actually under which conditions your blood would become acidic? When is this important? Yeah? When you exercise a lot, yes, absolutely. Why? Yes, you produce carbon dioxide, that's right, and you produce lactic acid. That is when your muscle ache. Yeah? That is when your blood pH could go down. Metabolic issue? Not everybody is exercising, as you can tell. If you suffer from diabetes, diabetic people always struggle with keeping their blood pH constant. Why? Because they don't use sugars as fuel. What do they use instead? What do they use instead? Instead of sugar? Loud? Who said?
Is it glycogen?
No, they don't use glycogen. What do they use instead? No. They use lipids, exactly, fatty acids. And the oxidation of fatty acids produces acids. And these acids make the blood pH go down. Yeah? Can you imagine what happens, how you would increase the pH if you didn't have the buffer system? Any condition? Yeah, but what conditions? Like, you're right, it would result in the denaturation of enzymes, but under which condition would your blood pH go up from 7.2 to 7.4, for example? Yes, but usually humans don't tend to do anaerobic respiration. If, for example, you throw up a lot, you remove acid from your system, from your stomach. Yeah? Another thing is, you earlier mentioned the carbon dioxide. If you exercise a lot, you accumulate carbon dioxide. That makes your blood pH go down. If you are hyperventilating, let's say in an exam, you remove the carbon dioxide. Yeah? When you remove carbon dioxide, you have less acid in your system, your blood pH would go up. So there are real consequences why it is so important to have a good, well-working buffer system. So next time you go in an exam and hyperventilate, think, no, it's not good, right? Just to deep breathing. Have you actually done that? Has anyone told you about that? Fantastic trick to overcome stress and anxiety. Shall I tell you? It's very simple. Breathe in on the count of 5, to the count of 5. Hold your breath to the count of 7. Breathe out through your mouth, count of 8. Do that 5, 6 times. You will feel much calmer. Did you just pass out? If you pass out, it wasn't my fault, right? This is a trick, actually, which is called deep breathing. If you are stressed, if you are anxious, try that. What it actually does, it calms down your nervous system and your breathing regulation in your brain. It also regulates your pH in the blood. And this pH, if it is out of balance, it triggers actually anxiety attacks. So with this deep breathing technique, you bring it back to where it should be. Okay. We have a 5-minute break, and then I'll tell you what you do in the practical.